giving me the opportunity to present my work here. As Simon said, yes, I am a postdoc student at the University of Twente, and I'm going to briefly go through what I want to show you today. So we are going to talk about excitons. We are going to talk also about where the heterogeneity comes in those perovskites from, and how we can basically categorize it, and how it affects the excitonic properties. I plan to go through both 3D and 2D double perovskites. This is the focus of my research. Let's see how much time I really have, but yeah, so that's the plan, to go through both 3D and 2D. I think that the keyword in my title is really first principles. So I think that you might have heard from about everything in my title, more or less, but what I want to make known and stress a bit is the first principles keyword, and that's basically because I am a theoretical physicist. So what I am doing is theoretical spectroscopy for complex materials. Now, I have some equations, 3. That's all, more or less all the equations that I have. I want to go into any great detail, but just to briefly show you the method that is behind the results in the research that I'm going to present today. So what I am doing is to look into optoelectronic properties of perovskites, and I'm doing this from the theory perspective. So I'm using the density functional theory as a starting point for the electronic properties. Now, these have a disadvantage that the band gap that we get from DFT is highly underestimated as compared to the experimental band gap, especially for perovskites. And then we basically need something else to improve those electronic properties that we get. So at the bottom of the slide, I have a scheme that summarizes the basically each step of the workflow that I'm going through. So first we get DFT band structure in gray. Then the next step is to do GW. That's an approach that is well known to give rise to more accurate band gaps and electronic properties. So that would what I do in practice is basically to get the eigenenergy that I get from DFT, and then to correct it with this term, basically this term that contains the self energy and the exchange correlation potential. So when you do this, then you get a more accurate electronic picture, so band structure. This is here represented in black, and then you get an opening of the band gap very well. Then you get your electron and hole, but no interaction between them. So in order to get optical properties, you need to get interactions to include the interactions between electrons and hole. And to do that, I am using the Bethe-Salpeter equation formalism. And when I do that, I explicitly take into account the interactions between electron and holes in the material that I'm interested in. And by solving this equation, I get absorption spectra and absorption coefficients of the materials that I'm interested in. I also want to show you very briefly a scheme that basically summarizes the workflow that I just talked about. But this is made basically to give you an idea about how expensive those calculations are. So this is an example for a double perovskite using more than 2,500 CPUs. And on x-axis, we have the time to solution, so how long the calculation run until I get the result. And on the y scale is the memory that needs to be available during the calculation for each step. So you see that the first part, the mean field calculation, the starting point takes about 1 day. Then those quasi-particle corrections that lead to more accurate electronic properties, that is another 3 to 4 days usually, and also the memory requirements increases drastically. And then I go to the Bethe-Salpetre equation, then I include the electron hole interactions, and that is more or less 10 days. So in total, if we add up everything, then a calculation to get an absorption spectrum for a material that requires around 2 weeks of execution, basically on a lot of CPUs. And yes, with this, so this is basically the background of everything that I'm going to show you today. And I don't think I need to really introduce perovskites to this audience, but what I want to quickly say is that the most well-known lead-based 3D perovskites, they are well known for solar applications, but it is also known from literature that they are not very stable under ambient conditions, and there have been mitigation strategies introduced in literature. Some of them are based on chemical substitution, either homovalent substitution, that means that you would replace lead in the, let's say, the most well-known MAPI or cesium lead iodide. Then you would replace lead with another divalent metal. So then you can go to tin or germanium, for example, but those were also not very stable. Nowadays, there is a lot of progress into this field, but so that's basically one way of mitigating the stability issue. And then the other way of doing this chemical substitution is the heterovalent substitution. And that basically means that we can replace lead with a combination of 2 metals, monovalent and the trivalent metal, and that would give rise to the so-called double perovskites. With these perovskites, those are still 3D variant, 3D materials. Then another mitigation strategy to increase stability is also to reduce the dimensionality. And with this procedure, you basically go to the 2D perovskites. You can do this with a single perovskites or the double perovskites as well. And then you get single or double 2D perovskites. Now, doing this, you will get materials with larger band gaps and higher exciton binding energy, sure. But the perovskites are not used only for solar cells. so they are still interesting materials. We can still use them for LEDs or photodetectors, and they are still very interesting class of materials to be analyzed. So what I'm interested in is double perovskites, 3D and 2D, and but those have a lot of heterogeneity in the crystal structure. And this heterogeneity can be categorized into chemical and structural heterogeneity. And as I said, when you go from the single perovskite to the double perovskite, then you replace the metal, and then you have now in the crystal structure alternating octahedra. Then the formula is now A to B, B dash X6, where B and B dash are the two metal sides. And this alternating octahedra pattern, this basically introduces chemical heterogeneity into the system. The next step would be to reduce the dimensionality, and you do that by intercalation of long organic molecules, and that would introduce another type of heterogeneity into the system, and that's what we call structural heterogeneity, because it really comes from the fact that you have two different layers, an organic layer and an inorganic layer into your material. And now, since we see that those are highly heterogeneous materials, then the next question is how does all this heterogeneity impact the excitonic properties? And this is something that the underlying question that we try to solve in our group. But yeah, so talking about excitonic properties, we first have to know what an exciton really is. And for this, I always use this very simplified scheme to explain what we call an exciton, what we think of when we say exciton. Now, this is a representation of a semiconductor with parabolic bands, and so those are the parabolic bands. Here is the valence band region, now the conduction band region, and they are separated by the gap energy. In the valence band region, we have excitons, nothing in the conduction band. But now, if we excite this material, this semiconductor, then the electrons would promote to the conduction band, and they would leave a hole in their place. What we do, and what our approach allows us to do, is to basically simulate exactly this scenario when the electron that is now in the conduction band does not fill the hole in the valence band. And if we go back to the double perovskites and take as an example the silver bismuth double perovskite, and compute the absorption spectrum of this perovskite in this particular scenario, then we get the black curve that is represented here. So now we don't take into account any electron hole interactions, but we can also do that. So we can switch on those interactions, and then we get the red absorption spectrum. So from this, we basically can compute the exciton binding energy, that is basically the difference between the energy of the first excited state and the energy of the direct gap of the band gap of the material. So we can now take a closer look to this absorption spectrum for this particular double perovskite, and for this I replotted it in order to compare it with the experiment. So this is an experimental absorption spectrum that is basically I got it from literature, from this paper down here, and what we can see and what we can say only by comparing those two spectra at first glance, we can see that the line shapes are very similar. So our theoretical approach yields pretty accurate absorption spectrum. We can also analyze the spectrum that we get in more details, and we see that the absorption, the excitonic peak here comes from direct transitions between the valence and the conduction band at X point in the Brillouin zone, and this is a resonant excitonic peak. We can also distinguish the fine structure of this peak, and in this particular example, this is made of 3 degenerate bright transitions. They are all here, and they give rise to this sharp peak. And there is another dark state that is basically localized before the excitonic peak. Now we want to basically try to characterize more these excitons that we see, and not only in one double perovskite, but in the entire family of double perovskites. But in order to do that, we start from what we know and what is out there in literature, and that's the lead-based perovskites. And those, we know that they are direct bandgap semiconductors, and they have parabolic bands and very dispersed bands, and we know that they have hydrogenic excitons. That means that the excitons in the lead-based double perovskites are very well described by the Wannier-Mott model, and this is basically a phenomenological model that allows to predict or to calculate the exciton binding energy using this formula here, and the exciton extent with the formula down here. And what it says, so this is a picture of the lattice, the crystal lattice in real space, and what you see here is that the electron and the hole, they are very far apart, and then the radius of this exciton is big. It spans multiple crystal points in this lattice. The question is, and also another important point that I have to mention is that the exciton binding energy in those lead-based perovskites is small, and is in terms of 50 millieV. So, but that is not true for double perovskites. For the double perovskites, the exciton binding energy is around, or at least for the silver bismuth, that is around 250 millieV, and that's almost as big as the exciton binding energy for the layered lead-based perovskites. And then the question is, can we now describe the and predict the exciton binding energy of double perovskites also with the Wannier-Mott formula? Are those still hydrogenic excitons, even though the exciton binding energy is big and the bands are not parabolic? Can we still apply the same theory that we know from literature? And what we did to try to answer this question was to first take a look. So we now vary the B and B dash sides of the double perovskites with basically, so into B and B dash, we plug in those chemical elements, and then we have a variety of double perovskites, and we do our approach, we go through the entire theoretical workflow that I've shown before, and then we get a bunch of exciton binding energies. We do the same, so we compute those exciton binding energies with Wannier-Mott model as well, and then we get this picture over here, and we see that for some materials, the exciton binding energy that we get from our first principles calculation is very close to the Wannier-Mott one, but for some of them, those two are very different. And also the absorption spectra of those materials are very, very different. So the question is, why Wannier-Mott performs well for some of them and it fails completely for some other materials? Because they have the same packing with alternating octahedra. So what's so different in those materials? And we actually, in order to see that, we have to look into the Wannier-Mott energy formula, and more specifically into the quantities that are variable here, and that's the reduced mass mu and the dielectric constant. So if we look at the reduced mass, what we see is that some of those perovskites have very anisotropic effective masses. For example, the lead-based that has no anisotropy, that's a single perovskite that has no anisotropy in the effective mass. Then there are a bunch of perovskites that have parabolic bands with almost no anisotropy, and they are very well described by the Wannier-Mott formula. But there are also a lot of perovskites that have electronic bands that are not parabolic, and therefore they are not well described by the Wannier-Mott formula. The next quantity that we have to look into is the dielectric constant, and in here in the Wannier-Mott formula, it is assumed that the dielectric screening is constant in space, but this is not true for the double perovskites. And in reality, this is not a constant, but it's really a matrix. And what we did is to look into to link this with a screening length parameter, and we observed that the materials that have hydrogenic excitons, they all feature high or long screening length parameters. That means that the dielectric screening does not vary on the length scale of the exciton in these materials. Now that we've seen what how the 3D materials behave, I want to very quickly show you some results on the 2D and what happens when we reduce the dimensionality of the silver bismuth double perovskite. So when we do this, we basically have one or two layers of inorganic perovskite sandwiched between long organic molecules, in our case butyl ammonium molecules. So now for the 3D, we saw the band structure, we saw the absorption spectrum. We know that for for the 2D case, the band gap changes from indirect to direct, and this should affect the excitonic properties as well. And the question is, how does it affect the excitonic properties? And we again go to something that is well known. We again go to literature and we compare to the lead-based perovskites. In the case of the 2D lead-based perovskites, we know that the exciton binding energy decreases with the thickness of the inorganic layer. So as you increase the number of inorganic layers that are sandwiched between the organic cations, your systems approaches the bulk limit and the 3D limit, and therefore the exciton binding energy decreases and it saturates at some point towards the bulk value. Now, this is what you would expect from the 2D double perovskites as well. But what is really happening into those experimental systems that are available in the literature? So unfortunately for those, we don't have n equals 3 and greater. But for n equals 1 and n equals 2, when n defines the number of perovskite layers, then the trend it's not the same as the lead-based. And what's actually really happening is that, first of all, the n equals 2 features a higher exciton binding energy than the n equals 1. And the decrease is less steep, so it still goes to the bulk value, but all of those values are really higher as compared to the lead-based perovskites. And this is actually happening because the excitons in those materials are highly localized. So as you can see in the n equals 1, so those are the exactly same systems, only that now I don't represent here the molecules in order to, like, for clarity reasons. And in green here is the excitonic wave function. So what we see is that the exciton is localized within 1 or 2 octahedra maximum. And this is actually the reason why the exciton binding energy is so high in those materials. So we tried to explain the unusual trend that we see in the exciton binding energy. And first we looked into the effect of molecules, because we wanted to see if this is coming from molecules or not. And for those, we constructed model systems, distorted model systems. So we replaced the molecules with cesium, and we kept all the distortions as in the experimental systems. And repeated the entire theoretical workflow. So we have again the exciton binding energies for those model systems. But again, the trend is not the one that we expected. Of course, the absolute values are a bit different, just because the dielectric environment is a bit different, but that would not explain the increase of the exciton binding energy. And then we looked, that pointed us to look into the structures, because that means that it's a fundamental difference into the structures. And we actually saw that for the layered systems, there are 2 different well-known phases, Diane-Jacobson and Ruddlesden-Popper. The Diane-Jacobson one is characterized by perovskite layers that are ordered directly on top of each other, while the Ruddlesden-Popper have lateral offset. And you can actually see better from the top view. One has the checkboard pattern and the other one like a stripe-like pattern. And if we look at the experimental structures, actually From the side view, we don't see much, but from the top view, we actually see exactly the same thing. The n equals 1 is a Rutherford-Popper with a stripe pattern, while the n equals 2 is a Diane-Jacobson structure with a checkerboard-like pattern. And therefore, we actually did not compare apples with apples, and we have to do that. And to do that, we created another set of model structures, and in this case, undistorted ones. So we kept Diane-Jacobson phase for both n equals 1 and n equals 2, and repeated our calculations. And with those same structures, same phases, we actually get the expected trend in exciton binding energy. And if we compare it now with the lead based, is actually following the same kind of decrease towards the bulk value. So that I'm gonna skip the outlook because I am a bit late, but yes, so I'm just gonna conclude now and say that I have tried to show you how we calculate excitonic properties, and I showed that the 3D perovskites have very diverse excitonic properties, but now we can understand them, and we can basically predict them only based on the crystal symmetry and the band edge dispersion. And for the 2D materials, we actually are with our approach, we are able to get the same onset order in n equals 1, 2, and the 3D materials for as in the experiment. And I also show that the stacking pattern actually impacts the excitonic properties, and it has huge consequences for the exciton binding energy, the value of the exciton binding energy into the silver bismuth double perovskites. And I want to very quickly just thank all the people that helped me in this endeavor, the collaborators that I've been working with, my supervisor Lynn Leppert, and all the funding and the computational resources. And thank you for your attention.